Let's create our first circuit. Here we are connecting a lead to a first jumper wire, which will be connected to the negative terminal of our battery. Next, we will connect another lead to a second jumper wire for connection to the positive battery terminal. Now insert the first jumper's lead into the first hole of the first row in our mini breadboard. Make sure that the lead is placed firmly in the hole, but do not push it so hard that it is crumpled. Next, position a resistor with the first leg in the same row and the second leg across the gap to the row on the opposite side. We use a resistor of a value of 220 ohms, as this is the size needed to limit the current to 20 milliamps for a red LED powered off a 6-volt source. Once again, make sure that the legs are placed firmly in the hole, but do not push them so hard that they crumple. Now place the LED adjacent to or in series with the resistor. Ensure that the shorter leg or cathode is in the same row as the second leg of the resistor, facing towards the negative terminal of the battery. The longer leg or anode must then be placed in another row towards the positive terminal of the battery. Now we complete the circuit by placing the second jumper's lead in the same row as the LED's anode. Finally, connect the second jumper wire to the positive terminal of the battery, which is the red wire, and connect the first jumper wire to the battery's negative terminal, which is the black wire. Voltage is applied, and as you can see, the red LED lights up as the anode and cathode are connected the right way around, and the current is sufficiently limited to prevent overheating and damage. Now let's see what happens when we reverse the polarity of the circuit. Disconnect the jumper wire from the battery and now attach the second jumper wire to the battery's negative terminal and the first jumper wire to the battery's positive terminal. We will see that the LED no longer lights up. This is because the positive terminal of the battery is now connected to the LED's cathode and the negative terminal of the battery is connected to the LED's anode. So current will not flow as the diode acts as an open switch. Now let's look at our battery holder containing 4 1.5 volt cells and check their voltage with this multimeter. On the left hand side you can see the scale for the voltmeter setting, which we will set to a limit of 20 volts as we expect a reading of around 6 volts. Now we will connect 1 voltmeter probe to the positive terminal of the battery, which is the red wire, and the other voltmeter probe to the negative terminal of the battery, which is the black wire. On the screen, you should see a reading of around 6 volts. Notice that in this video, the reading on the voltmeter screen is shown as a negative value. This is because we have reversed the polarity by attaching the red probe to the negative terminal and the black probe to the positive terminal. Looking at our multimeter again, we see the voltage settings lie on the left-hand side of the dial and the current settings on the right-hand side. We will set the limit to 200 milliamps. If you wish to measure the current in a circuit, you need to place it in series. This means positioning it adjacent to the other components in the desired current path. The ammeter has negligible resistance, so will not significantly affect the current being measured. You can see that the current flowing through the circuit we built is 18.9 milliamps. This makes sense as we have designed the circuit to have a safe operating current of 20 milliamps. Amps is the unit used to measure current or rate of flow of electrons. Now we are going to keep the same circuit but reposition the ammeter from one end of the circuit to the other end of the circuit. It will still be placed in series with the resistor and LED, But now we'll measure the current after it has passed through these components. You will notice that the current reading is practically the same as our previous reading, which confirms that the current is the same at any point in a single path circuit. Now we are going to take the same circuit and measure the volt drop across the resistor. Notice how we have set up the circuit so that the voltmeter sits in parallel with the resistor. This means one probe is connected on one side of the resistor in the same row as one leg, and the other probe is connected on the other side of the resistor in the same row as its second leg. The voltmeter has a very high resistance, so current prefers to flow through the resistor rather than the voltmeter itself. As expected, the volt drop across the 220 ohm resistor with a current of 20 milliamps flowing through it is around 4 volts. We will look into how to actually calculate these values in video number 2. Now taking the same circuit for our last investigation, we will measure the voltage drop across the LED. Once again, the voltmeter is set to a limit of 20 volts and is placed in parallel to the LED in the same way we did for the resistor. As the resistor and the diode are only two components in the circuit with significant resistance, it makes sense that the sum of the voltage drops across them would be equal to the voltage being supplied by the 6-volt battery. We can see on the voltmeter screen that the voltage drop across the LED is around 2 volts, so this seems correct.